Good day, everyone. I am January de Guzman, and I am here to present our project, our paper, together with my team here from the College of Engineering Technology at Batangas State University, the Philippines National Engineering University, Mr. Junmar Bay, Engineer Angelica Delisay, and Dr. Edsel Toralba. So our paper is entitled Integration of Temperature, TDS, or Total Dissolved Solids, and Turbidity Sensors for Water Quality Monitoring and Machine Learning Application. So let us proceed with the introduction. So water is indeed essential to sustain life, and a satisfactory, let's say adequate, safe, and accessible supply must be available to all. Improving access to safe drinking water can result in tangible benefits to health. Definitely. That is how water is essential. Every effort should be made to achieve drinking water that is safe as practicable. That is according to the World Health Organization in 2017. That is why water quality monitoring is a cornerstone of sustainable environmental management. Traditional methods in water quality monitoring could be time consuming and laborious. That's true. It sometimes requires field collection, lab analysis, more more. So our research proposes a modern alternative for that uses a real-time IoT-based system to measure temperature, total dissolved solids, and turbidity in private water supply systems. And of course, the data gathered from those sensors mentioned are used or further utilized for machine learning application for water quality classification. But to emphasize our objectives, first, this study specifically aims to integrate the temperature, total dissolved solids, and turbidity sensors for gathering water quality parameters. So we want these three sensors to work together in gathering valuable data that can be used in order for us to monitor water quality. Okay. Our second objective is going to be to deploy the integrated system in a private water supply system. That is already a complete integrated system. When we say complete integrated system, it is a working system. It is a working system that gathers water quality parameters uh, in a specified time interval, and then transfer that data into a database. Okay, and then develop a water quality monitoring system, of course, based or from those data, and then a machine learning model from those data, specifically water quality classification. And then also part of the study is to test the performance of the machine learning model that has been developed. Okay, but in order for us to do that, we need to uh, have a systematic approach towards those objectives. So that is why we have this methodology. The methodology used in the study is a waterfall methodology, and it is represented here in this illustration. So, and then, as shown in the methodology, we want to present here the system design. So this is a very straightforward design of this kind of system, an integrated system. So we have here uh, a private or household private water supply system wherein uh, the system is deployed. And then our system, of course, as mentioned, we use three sensors: temperature, total dissolved solids, and turbidity sensors, which are gathering water quality parameters from the household water supply system. And then it feeds it to the Arduino Uno, wherein we also do the programming here for the sensors. And Arduino Uno transferred it to ESP8266, which is the Internet of Things really comes into the play or comes into the system. And then from the ESP, it transfers the data to a database, or it stores the data in the database. And the data that are collected uh, can now be used for quick monitoring, of course, since those data can immediately indicate something. Let's say there is a high turbidity reading, then it can definitely be used for quick monitoring. But as part of the study, as mentioned earlier, we also want to have or to develop a classification machine learning model, actually a supervised classification machine learning model. So here Basically, this is how a random forest algorithm for machine learning works. And this is the actual deployment or development, sorry, development of the machine learning model in Jupyter. So we also use Jupyter, we actually use Jupyter frequently for training the model. And then here is the deployment of the machine learning model. After developing the machine learning model, we are able to deploy it in a local development environment in our local devices. So here, this is the actual screenshot of the machine learning model that is able to say or classify whether the values in TDS, turbidity, temperature altogether is safe, unsafe, or fair. And then on this part, this is actually the GUI that we developed, wherein you can input data and the machine learning model can classify whether it is unsafe, safe or fair. And based on the data here, it is able to predict it as unsafe. And then for the performance uh, matrix that we use in order to assess the performance of the machine learning model. So we use the precision, recall, and then of course the F1 score. So as you can see here, for these are the samples, fair, safe, and unsafe. This is what the model wants to classify, and its precision score is one, showing that out of all the samples, it is able to predict it correctly, 100%. And then for the recall, so this is the score is also one for each classification, which gives us a score of one as well in F1 score. And by the way, the data is split by 80 to 20, 80 by 20, meaning 80% for the training set, and the 20% is for the uh, test set. So the accuracy uh, metric is used in the test set only. So basically this is the test set evaluation. Also did confusion matrix on the test set as well. So as you can see here, out of all fair, the machine learning model only missed one or misclassified one, or I mean two. It misclassified two, and for the actual safe, it uh it accurately classified every safe uh, sample, and in unsafe, it only missed one. It misclassified only one sample for the unsafe. Okay, that is how the confusion matrix works. And then we also have the stratified cross validation test for the entire sample. So the results are here. So we have zero point 0.9 or 93%, 95%, and but we have 67% only. This is due to imbalances in the data set because the total number of samples that we have in our data set is almost 38,000 samples, and there are imbalances there because as you can see in the class distribution for the fair, we have 23,565 samples, which is 61.5% of the whole data set. And then the unsafe and safe is 24.2 and 14.3% only. This is due to the unpredictability in water conditions, really, in the actual setup or the actual environment that we deploy the model. And then for this project, these are our conclusions. So we successfully integrated temperature, TDS, and turbidity sensors into a real-time monitoring system. The system provides water quality data for private household water resources. It enables quick classification of water as safe, fair, or unsafe. And the machine learning model which uses random forest shows excellent classification performance. And it supports, of course, the whole project supports health by ensuring water safety through timely alerts and data interpretation. And then it provides a scalable foundation for future water quality innovation. That's all for the presentation of our paper. The integration, let's go back at the beginning. The integration of temperature, TDS, and turbidity sensors for water quality monitoring and machine learning applications. Thank you for listening. system